Let us now see the design of the reinforcement in the stab. We have already found out that the factored moment mu is 405.16 into 10 to the power 6 Newton mm. Okay, so we know this AST equals to 0.5 FCK Fy and so on. Let us substitute all the values of the parameters we know, that is FCK, Fy. B we are going to take as 1 meter, that is 1000 mm, and the effective depth is 440, that is the entire depth, overall depth we had considered as T as the effective cover, we get 440. So this is 500 minus 60 will give us effective depth of 440 mm. When we substitute, we get the area of steel as 2967 mm square. Let us use 20 mm bars, and the area of 120 mm bar is 314.1 mm square. So the spacing small s is calculated as, for every 1000 mm, the spacing of a 20 mm bar required, okay, divided by the area of steel that we need to provide, 6 mm. Okay, so the spacing required of a 20 mm bar is 106 mm. Let us provide 20 mm bars at 100 mm center to center. So when we reduce the spacing from 106 to 100 mm, the actual area of steel provided is calculated as 1000 mm into the area of 120 divided by 100. Okay, so this is 3141 mm square. All these bars can be bent in the toe slab to serve as the reinforcement for the toe. So sufficient bond length, okay, beyond the point C, where the maximum bending moment occurs in the heel slab. So we have this point here C. Okay, this is the heel slab, this is the toe slab. When we are designing the stem slab, we should know that this part here, okay, the point C, experiences the maximum bending moment. Okay, however, we cannot curtail the bars or stop the bars there or cut the bars at that point. So in order to ensure sufficient bond length, what we do is we take this reinforcement like this, okay, and we can either continue it like this here, or we could continue it on the top of the toe slab. Okay, so say for example, I'll draw it with another color. Okay, so it could be continued on top depending upon which side experiences tension. Next, let us find out the total shear force at C. So we know that there is a horizontal force due to a person standing, which is Q. Ka into W into H1 is the horizontal force due to the traffic load, and Ka gamma H1 square by 2 is the load due to the backfill. Okay, so we are calculating the load at C, so keep in mind that we are going to be using only the height of the stem here, so that is why H1 is 5.5 meters. So we get the total shear force at C as 125.75 kilonewton. Now we need to find out the shear stress that is experienced by the stem, and it is given by tau suffix V. It is this is an unfactored load. 125.75 is unfactored, so because of that we are adding a factor of 1.5 here multiplied by the unfactored load 125.75. this is in kilonewton. To convert it into newton, we multiplied by 1000 divided by B into D. Okay, so the formula is nothing but force upon B into D. Okay, so it is actually Fu. 125.75 what we had calculated was F. Okay, so to multiply, to convert it into a factored load FU, we multiplied by 1.5. To convert it into newtons, we multiplied by 1000. So B is 1000 mm and D is the effective depth, which is 440 mm. So we get tau V as 0.429 Newton per mm square. Next, in table 19, in order to find out the permissible shear stress in the concrete, we need to find out first what is 100 AS upon BD. AS is the area of steel which is provided, and we have calculated it as 41 mm square, and B and D 1000 and 440 mm respectively. So this is the percentage of steel that is provided, and it is 0.714%. So corresponding to M20 and 0.714, tau C from that table works out to be 0.55 Newton per mm square. So this value is how much shear stress the concrete can take depending upon what grade of concrete it is and what how much amount of steel you have provided, and tau V is the amount of shear stress that the section is experiencing. So tau C should always be greater than tau V. If not, then we have to provide shear reinforcement, or we need to increase the section. So in this case, the permissible stress, or the amount of stress, shear stress that the concrete can take, is more compared to what it is currently experiencing. Therefore, it is safe in shear. Next, the author has explained how we need to curtail the main reinforcement in the stem slab. I will not be going through this, but you can go through the PDF that is attached, and this is more of a trial and error method to know where you can curtail the reinforcement. So what the author has found out is that half the bars can be curtailed at a height of 3.2 meters below B. Okay, so B is the top of the stem, and half of the bars, so if it is 20, we had provided 20 mm at 100 mm center to center. So at this particular distance that the author has mentioned, we can curtail half of the bars. That means from above this point, it will be 20 mm at 200 mm center to center. That means you're curtailing every alternate bar. I will next move on to the distribution reinforcement in the stem slab. So the author has found out the average of the thickness of the stem. So at the top it is 200 and at the bottom it is 500. So the average of it is 350 mm. So area of distribution reinforcement is 0.12%. This is B and this is D. Okay, so the average, and it is 420 mm square is the distribution reinforcement. If we are using 10 mm bars, using the spacing formula, we get it as 186 mm center to center. We can provide 10 mm bars at 175 mm center to center at the inner face of the wall along its length. Okay, so main reinforcement we have already calculated, and it is, so this is 20 at 100 mm center to center, and then what we have just calculated is the distribution reinforcement, and it is 10 mm at 175 mm center to center. So these are on the inner face. On the outer face, we need to provide to take care of any changes due to temperature, and we provide the minimum reinforcement of 420 mm square, but this is divided along both the directions. So we can provide 10 mm bars at 350 mm center to center both ways on the outer face. So this is how the stem is designed for inner face reinforcement and the outer face reinforcement. This is what the detailing of the stem slab will look like. So here it is 20 mm at 100 mm center to center. So 20 mm bars at 100 mm center to center. Okay, and as we have discussed, 3.2 meters below the face B, the author has curtailed the bars, that is from 20 at 100 mm he has now provided 20 at 200 mm. That means every alternate bar is stopped at this particular point. Also, if you see the dotted reinforcement, okay, which runs along the length of the stem, it is distribution reinforcement and it is 10 mm at 175 mm center to center. So this is on the inner face. On the outer face, the reinforcement is divided. The distribution reinforcement of 420 mm square is distributed in both the directions. So 10 mm along the face, 10 mm at 350 along the length of the wall, and also perpendicular to the length of the wall. Okay, so this is temperature reinforcement.